Okay, it's working. So thank you for having me here, and especially Stefano, because he twisted my hand, you see, in order to make me talk. See, and anyway, so I'll be talking about fermions in the unitary regime. This is a system which is extremely popular lately. I'll tell you a little bit about the story of this, you see, because I assume that not everybody is familiar with the topic. And then I'll talk about what I've been doing. I started myself doing this type of calculation actually in 2004 with this young fellow who was the graduate student at the time. He started working with me. And I often or sometimes I do the following. When a new graduate student comes to me, I decide to find a topic which is completely unfamiliar to me. It was completely unfamiliar to him, obviously, because he is a student. And we started, and within a month or two, Piotr, who is sitting here somewhere, you see, joined us. And basically, this formed the nucleus. Later on, Gabriel, which was a student of Piotr, joined us. Now, this fellow and this fellow, they are both assistant professors. And now Kenny Roach joined this effort, because we put all this project now on parallel computers and in order to study bigger systems. And I'll talk a little bit about that, but not much. I won't stress that part. So this is a list, you see, which I made, you see, because I don't have a content. But basically, this are the papers we published since then, and it's actually the topic. Some of them I'll be covering. And I'm not entirely sure the list is complete. But we covered quite a lot of topics. It's in the reverse chronological order. It starts from here and goes up. So we started with the thermodynamics of the system. Then we looked at crossover phenomena, BCS. I'll tell you a little bit what that is. Then we look at the pairing properties. Then we looked at viscosity, transport properties, and a bunch of other properties, which I'll be mentioning in the talk. So now, first of all, I start with an introduction. You see, what is this system? The unitary Fermi gas. So the problem started, at least for the theorist, to some extent here in Seattle by George Birch in 1990. There was a conference, many body 10, and then he issued a challenge, which is this one here. Says, what are the ground state properties of the many-body system composed of spin 1/2 fermions interacting via zero-range infinite scattering length contact interaction? The problem with this is that this particular problem is an idealization of the neutron, dilute neutron matter, because the scattering length for neutron-neutron scattering length is very large. It's almost 20 Fermi. And the range of the interaction, it's of an order of magnitude less. So in principle, like any theorist, respectable theorist, you take the limit. You took 1 to infinity, 1 to 0. And this is realizable in principle in the crust of the neutron stars. Now, for the theorist, this was a challenge. So now to remind you, see what is the scattering length, because maybe not everybody thinks in those terms. This is an old formula, I think, goes back to Bethe in the 1930s. He parameterized the phase shift of the S-wave phase shift in this way. This is the scattering length, this is the effective range. So the system will be looking at when this is infinite and this is 0. And what happens in that case, delta, the phase shift, acquires the maximum value, which is pi over 2, and therefore the cross-section becomes maximum possible, given by quantum mechanics. And this is the reason why this is called unitary Fermi gas. It's the largest possible cross-section. In the limit, when k goes to 0, in principle, this could become infinite. So this is that. Now, why is this interesting, at least for tourists? So let me make a parallel here with the old problem. So let's assume that we want to calculate the energy of the hydrogen atom. If you wouldn't do any theory at all, you'll express the ground state energy as a function of these 3 constants, because obviously there is nothing else there. And the only dimensional quantity which you can create, which has dimension of energy, is this. This is the only combination possible. And you need quantum mechanics in order to figure out the coefficient of order 1 in front. So this is where the hard work is. So in principle, if you know this, you know that. Now, for the unitary Fermi gas, we have a similar problem. So if we have dilute Fermi matter, the ground state energy in a given volume or a given number of particles can depend only on this. It's a function of these parameters. Now, where this is the mass. Now, if we take this to infinity and this to take to 0, this function becomes this one. And now the only possible combination of these quantities, which has dimension of energy, is this, where this is the Fermi energy defined in the usual way. So now the problem is, what is this constant? Obviously, for free Fermi gas, this is 1. Now, we turn on interaction. So then when we turn on interaction, we come back to this problem. We have this infinite, this 0, and this can be realized only if you have attraction. So the energy can go down only. So this has to be smaller than 1. Now, if it's smaller than 1, the question is it positive or negative? Because if it's negative, you can minimize this energy by increasing the density. So in principle, the system will collapse. But if it's positive, this is a system. It's a gas which can be contained in a container. So it will exert pressure on the walls. So at that time, in 1999, it wasn't known what was the sign of it. So here I have a little bit about that. So there were papers which I, on purpose, you see, don't show, which were published, which contain contradictory results. Some of them proved that the energy of the ground state is negative. Some of them proved that the energy of the ground state is positive. So you didn't know the result. If you'd have bosons instead of fermions, the system is unstable. It will collapse because of the Efimov effect. If you have not spin 1/2 fermions, but for example, you have neutrons and protons together, and forget for the moment of the Coulomb interaction, the system would collapse as well. So if you have more than 2 species, 3 species, the system collapses. Now, if you are in 2 dimensions, you don't have a collapse. If you are in 4 dimensions, then you have a collapse. So for 3 species and so on. So the system is very, very strange. So that challenge, which George issued at the time, came with the prize from his own pocket. He put $300 there, and then Victor Caudle added another 3. And this fellow, George Baker from Los Alamos, presented an argument which was pretty good at the time, that the system actually is stable. So that means if I go back here, if I go back here, this is positive, but smaller than 1. He gave estimates of that quantity with some relatively big error bars. In 2003, Carlson et al., so it's Carlson, Kevin here, Pandari Pandey, and okay, sorry about this. You see, I know this by heart, so I have lapses. They actually provided the first fixed node green function Monte Carlo estimates of the ground state of this system, and I'll go very quickly through that. A year later, a group from Trento did the same thing. And also, almost simultaneously this was in December of 2002, and this was early 2003, I don't remember exactly the month. They demonstrated this system experimentally. How this was done? Okay, so I'll cover that in a little bit. But what Carlson et al. Have done, they determined this number here, and at the time I think this was 44, not 40 here, so it was a little bit higher. So this is a later estimate, and nowadays it's a little bit lower. But at the same time, they proved one more thing, that the system is superfluid. And the pairing gap obviously has to be proportional to the Fermi energy. This is the only physical quantity with dimension of energy in the problem. And this has to be a word of 1, and this is 1/2. This is enormous gap, enormous gap. Okay, so it has a huge pairing. The system is strongly interacting because basically the elementary cross-section, to some extent you can say it's infinite. But at the same time, the system behaves almost like a free Fermi system. So it's really very curious. Yeah.
Was there any doubt that the system would have been superfluid?
That's a very good question, because the arguments which people presented at the time, I think, were based only on the Leggett arguments. And Leggett arguments are mean field. And if you apply mean field correctly to the unitary gas, you obtain the collapses. So that was one of the papers which I didn't show. Okay? So I don't know if you see what to say. Okay? And it was actually the earlier paper by Eagle. You see, Eagle and Leggett. So, pass your judgment.
No one remembers that.
Yeah. So, to me, this is the proof. This is the first time when it was proven.
Because
Consistently.
in some textbook you find the statements like which go like any weak attractive interaction at sufficiently low temperature.
Oh no, that's absolutely true, but the system collapses. And once it collapses, you see, we don't know the properties of that system because the size of the system is 0, so then we have to do completely different analysis, finite range interaction and so on, and then we have to think. And not every system which has attraction interaction, look at atoms. They're not superfluid.
Depends on the temperature.
Huh? Atoms are not. You see, you have attraction between electrons and protons. You see, you have molecules. You see, not all substance and not the word.
I think the theoretical argument is that at sufficiently low temperature.
That's solid helium.
Not all electronic systems are superfluid.
No. Never.
No.
I've got to.
No, it's not true.
It's
That's a
it's
that-
mod phase.
yeah.
That's the whole model.
Yeah, so there are all kind of things. So I think you see so I didn't quite get, you see, I tell you a little bit more. So it's a long discussion anyway. So now the system we are looking at, it's very dilute. This condition is fulfilled. We're going to take this to 0. At the same time, it's strongly interacting. This is infinite. But there is a region, even for systems, real-life systems, where the interparticle distance, which is basically half of the Fermi wavelength, it's somewhere in between these two. And now, apart from the unitary Fermi gas, we can study the unitary regime when these conditions are fulfilled. So the interparticle distance is much smaller than the scattering length, but at the same time much larger than the radius of the interaction. So this will be the system I'll be talking about. Now, in cold gases, one can control the strength of the interaction. And then you can have basically any scattering length you want. How you do this? You take lithium-6 atom in the ground state, and that's a it's a fermion, right? Sorry, see, I had to count in my mind. You see the now protons, neutrons, and I forgot the neutrons. You see, that's the story. So there are 9 fermions here. Yeah. Now, if you put this into a strong magnetic field, what do? The geomagnetic factor for the electron is much larger than the one for the nucleons. So the nucleons will give you this splitting. You see, the ground state of lithium-6 is spin 1, so you have a triplet. But at the same time, the electronic spin points downward, and the nuclear spin can point in 3 different directions that you populate these states. Now, you reverse the direction of the electron spin, and then you have the other triplet. So these are the hyperhand structures. Now, you populate these 2 states, this one and that one. And then you look at the interaction between 2 atoms. You see one in this state, one in this state. As a function of the magnetic field they're embedded in. So this is like a universal ether, if you want, which fills the space. And depending on that, you see they interact. This is how the scattering length, this is calculated, behaves. At this value of the magnetic field, 834 Gauss, the scattering length is infinite. So you vary a little bit to the left, it's positive. A little bit to the right, it's negative. This means that in this region you have a bound state, in this region you don't. Now, if you go all the way here, the scattering length goes to 0, negative. That's weakly attractive interaction. You go in this direction, that's weakly repulsive interaction. And in this way, you have a crossover from BCS to BEC, simply by changing the magnetic field. So this is how you can control it. Now, in experiments, they confirm it. This is how it is. And actually, this is the Hamiltonian used in order to do these calculations here. So probably I'll skip this and not go through these details unless you really want me to do it. Okay. So this is known. And anyway, so there is a closed channel, an open channel. There is whatever interaction, but actually you get the desired effect that the scattering length goes to infinity. The problem which we have now is the following. we can vary the scattering length, and it's convenient to study the problem as the inverse scattering length. And this is the unitary case, unitary regime, it will be somewhere here. If we have slightly attractive interaction, we get the BCS. Okay, this is what you just mentioned, and that's known. You get slightly repulsive, but this is also attraction, because actually how you get that? You increase the interaction, you form a bound state. At that point, the scattering length is infinite. You increase the interaction further, the bound state goes down, but the scattering length becomes positive. Okay? So at this point, you form dimers. And these dimers are bosons. Now, they have a very small radius of the order of the scattering length. They are very far away from each other. And this is a system of dilute bosons. So this is the BEC. So changing the magnetic field, you can change a superfluid from BCS to BEC, and then you go here in the middle, and the question, what the hell happens there? That was the question, as a function of temperature, more or less. If you increase the temperature high enough, obviously you'll deal with the normal system and you don't care what it is. But here, everything becomes interesting. This is perturbative, more or less. This is perturbative. This is not. Okay. 2005, experimentally, people observed quantized vortices in the system. So this was the ultimate proof that the system is superfluid. Okay? Now, how do we deal with this? So I'm interested in finite temperature properties. And work at finite temperature, finite chemical potential, because this was done. Principle one can do something else. Our object is to calculate this quantity, and maybe some other observables. The Hamiltonian, which we have, so we will have this structure. We have spin-ups, or one type of fermions. We see one hyperfine structure. So if I go here, so this is spin down and spin up. So these are the two species. Okay. Okay. This is the kinetic energy, mass of the lithium atom, and the interaction between them, which in principle I can control with the external magnetic field. Now, I define in the usual way all the quantities, but since I have to do calculation of this, obviously I have to do the trotterization. You see, I heard this word at some point, you see, and I liked it, even though not everybody likes it, like, Council Trotter. So nothing unusual here. So everything here is right. There is a problem here, that if you have a short-range interaction like this, zero range, with a finite strength, if you calculate second-order perturbation theory with this, it's infinite. So you have to renormalize it. So you cannot deal with that, you see, simply like that. So you have to deal with this carefully. Now, we do deal with that by putting this on a lattice. Once you put it on a lattice, and I'll discuss a little bit about that, so it's a spatial lattice, you solve the two-body problem on the lattice with that interaction, and you have a relation between the strength of the interaction, scattering length, and the cutoff, which is defined by the lattice constant. Okay? So in principle, I can relate physical quantity with the one which I'm going to put in my theory, in my computer, knowing whatever the lattice constant is. So I have a running coupling constant. So if I take the lattice constant smaller and smaller, you see obviously this will change. This doesn't change. This is 0 if I'm at unitarity. Yes? Anytime you feel questions, ask, interrupt, please.
Yeah, maybe it's a little bit technical. As far as I understand, this procedure to map a continuous system to the lattice model is defined by associating the properties of the scattering states.
Mm-hmm.
And might there be a problem if I go deep in the BC limit?
Yes, there could be. So at the time when the size of the dimer becomes the size of the lattice constant, you have a problem. That's where you have a problem. So that's very simple. So at that point, what do? You make the lattice constant smaller, and then you go further.
It might be that this problem appears even before going to the extreme limit, because
It's where the scattering length is of the order of the lattice constant, within a factor of 2. That's where you have the problem. I don't remember the relation. I can derive it quickly.
I think one should be very careful here, because I again, the mapping, so this definition is based on the idea.
Okay, this is not on the lattice. Actually, this is done on continuum, where you put a finite cutoff in momentum. But then you can derive the same equation for the lattice, and it looks almost like this is a very small correction. And the correction depends on the size of the lattice. And if the lattice is large enough, I mean the box is large enough, that correction is exponentially small. So I hope that settles. Okay? So these are the two aspects there. So this is actually continuum with finite cutoff momentum, not go all the way to infinity. But you put it in the lattice, there is a correction which depends on 1 over L, which is the size of the box. Okay?
If you took the experiments and the actual length scales, since they're finite systems, would that correction be small in the experiment?
In the experiment, it's, you see, so let me try to give you some parameters.
The length scale.
Yes, so I'll give you some parameters for the experiment. The radius of the interaction between two atoms is the so-called Van der Waals radius, which is of the order of 30 to 60 angstroms, depending on the atoms. I don't remember what's for lithium-6, but it's somewhere in that ballpark. Interparticle distance separation between these systems, it's of the order of 3,000 to 6,000 angstroms. So that's the other one. Now, the number of particles they may typically make experiments goes from 10,000 to 1,000,000. So extract the cubic root from that, and you have the box size. So here you have at least a factor of 10, you see, ratio between these parameters. Yeah, that's more than enough. Okay. Any other questions? Oh, okay. Okay, so this is a problem here. So now the question is, if I'm going to put it on a lattice, how I'm going to choose the size of the box and the lattice constant. So the way to do this, you see, so let's set a particular physical quantity like the momentum distribution, which should have a distribution like this. You see, it doesn't matter, you see, it's more or less like this. Now, if I'm interested in seeing details at this scale, they are controlled by the box size. So making the box size bigger and bigger, I can make this scale smaller and smaller. So this is how the box size control is. If I want to go up to this momentum, this is given by the inverse lattice constant. So if I'm interested in whatever properties here, I have to choose carefully the size of the box, lattice constant, in order to reproduce those properties. Okay, so this is how we set the problem. Now, you can think of this in phase space. So if you do classical phase space, this is coordinate and this is momentum. This is the size of the system. It goes from minus L to L. In momentum, since we have fermions, we occupy states with significant probability from minus k to k. So you want to occupy this thing. Once you fix this, you fix the lattice constant. And this fixes the size of the box. Okay, so this is how we operate. Now, if we look at our properties, you see what we want to do. The cutoff is given by this quantity. So we want this to be much larger than quantity of interest. And this will be this. We want to have a certain resolution in energy, so that means the box size is this. And so on, you go through all these properties, and this is how you choose the system. Okay. Now, once you do that, I skipped a formula here. And if you want to see, I can do it quickly, derived, but I think I skipped it. I have the interaction. This is a two-body interaction. What I do, I apply the usual Harbach-Satonovich transformation. This is negative. The coefficient here is negative. So there is no problem. But actually, we do a little bit better than that. We do discrete transformation, which goes back to Hirsch, I believe. It's discrete in this case because this is on-site interaction. You need only one stochastic field. So it's a discrete stochastic field. Did I do it on the next slide? No, I didn't do it. And this is our stochastic field, which obviously, remember that I have a running time, imaginary time. I have a lattice point, so the stochastic field depends on those four coordinates. Okay. So if we want to calculate the partition function, we can represent it like this, where this is the evolution operator. The evolution operator has a usual structure, time ordered, but the property which is nice here, that if you take the trace of this, it's positive. And this is due to the fact that we have equal number of spin up, spin downs, and basically the propagator for those, both of them are the same, and you have one determinant for one determinant for the other, you multiply them, you obtain a positive number. You don't have any complex numbers at this point. Calculation of physical quantities, because this is basically, yeah.
So instead of on-site, if you had, let's say, a potential where Nx was here and Y was
We
there,
don't do that. This is zero range, you remember?
but if you had that, do you think there would be a sign problem?
That's another question. If it's attractive, no. If it's repulsive, yes. If it's polarized, it will be yes, because then I have chemical potential for spin up and spin down, which I don't. I have equal spins. So it depends on a number of things. Now, since this is actually mean field, everything is expressible through the density matrix, which has this structure, and these are simply plane waves. Now, how we do the calculation? We simply take all these plane waves, which exist in this box, evolve with this Hamiltonian, which basically is that, and then calculate this quantity. And then we calculate everything else. You see, this is how the calculations are done. Now, kinetic energy here, I'll talk a little bit about that. When people work on the lattice, they often replace, oh, here I had, you see, the Harvard-Unitary transformation, which I forgot, you see, so you can show that this is the expression. Okay? So they often replace this with the hopping model. Now, hopping model, it's the lowest possible approximation to the second derivative. Now, if you do this, depending on the direction, because this breaks the rotational invariance, the kinetic energy eigenvalues will be in this band here. The actual are this. We use the blue all the time. The reason for that is because when we do the propagation, we do the split between kinetic and kinetic energy and potential energy. If we apply the kinetic energy operator, we do a Fourier transform. After that, it's simply a multiplication, the application of the kinetic operator. And then we go back in the coordinate representation. That's again, it's a simple multiplication. So we don't have any matrix operations except at the end here. And I'll talk about this. Okay? But you see what the error could be if you use a Harvard model. You have a kinetic energy which is wrong basically in 7/8 of the space, momentum space, because this is about pi, this is the maximum momentum you can have. At about half, you have a decent approximation, but this is in one direction, three-dimensional. You see, it's 1/8. So basically, all this is wrong, and you underestimate.
You tune the U, right, correspondingly for different dispersions. So that's ultra.
Let me talk about that. You see, I want to calculate the properties of the system all the way from BCS to BEC. In BCS, U is 0. I cannot tune this.
Well,
okay? I go to BEC limit. You see, U is 0 there too. I cannot tune it. So that I don't agree. You obtain wrong the free Fermi gas, period. That's my statement. Okay. So we can argue about that, you see, as you want, but I don't think it's a controllable approximation, in my opinion.
Well, you could, I mean, the different, I agree they have different performances, but I'm just saying that it's not obvious that the Hubbard versus, you could also
you underestimate the kinetic energy. By how much, especially if you exponentiate this with temperature, this could be a big error. So in order to obtain reliable results, you'll have to have very low density, have the Fermi energy somewhere here, make sure you don't occupy. However, in a Fermi gas, the momentum distribution, this one, decays as a power law. So the tails are very long. So you are going to have effects of this no matter how much they are. So we can talk about this, how big they are. You can do this discussion a different way. Some people use this and they use a different relationship, and I think this is what you've done. Use another one which contains a quadratic term, which is the dispersion would go like this. And then you can bracket and say, you see, that gives me one error, this gives me another error. Why should I do 3 calculations when I can do 1? I do only the blue one. I don't have to do this. I don't have the other one, you see, in order to bracket, you see where the result is. I'll do only the blue one. And I think it's perfect. You see, if you can criticize doing that, you see, then we have a discussion. But the rest, you see, I don't want to discuss.
I mean, but your kinetic energy in outside the spherical cutoff, but
I have a cutoff in momenta. I don't have those things in the.
well, you said you did a Fourier transform.
Yes,
for the lattice.
yeah,
So
but
that
there's
will get
discrete.
you-
There's
yes,
discrete.
But then that will get you momentum numbers that are bigger. than-
No, it gives you up to cutoff.
What's that?
It gives you up to cutoff, not higher.
It gets
The
you
highest
up to-
momentum is it's 1 over the lattice
Well,
constant.
This is a cubic lattice, yes?
No.
Ah.
You can do both. You can do both. You see, so this is another technical detail. We can go through that. This is a spherical lattice.
Okay, that's. but-
If it would be a cubic lattice, the only difference which will be in this coefficient would be slightly different.
No, I understand.
But I
completely.
can do it that way too. And actually done calculation in both ways. There is no
With your
difference.
spatial lattice, where the Hubbard-Stanovich are on a cubic lattice or some other.
Okay,
strange
let me
lattice.
answer the question quickly, you see, because we can cycle into that, you see. We done calculation with cubic cutoff and spherical cutoff. There is practically no difference. If we satisfy the conditions which I listed here.
Okay.
Okay, so because otherwise we go in technical details. You see, I don't tell you about physics.
I mean, if you come in the afternoon.
I think there is interesting physics. You see, and I want to get there.
Okay, I'll stop talking. I can ask
Yeah,
you.
but I simply want to give you, see, some of the dirt. You see, because I think it's important to evaluate. Now, another thing is, you see, that we have to calculate these matrices here. You remember, you see, we have to take determinants and so on. The dimension of this matrix, it's actually the number of orbitals which I have. So how many lattice points I have, this is the dimension of this. So if I have 10 lattice points in this spatial direction, this is 1,000 by 1,000 by 1,000. Now, if I wouldn't have any interaction, I'll have only kinetic energy. This is simply the kinetic energy propagator. What would be the maximum value here? It will be beta. So the highest eigenvalue, it will be the cutoff energy over the temperature. The lowest one is 0 over the temperature. If I take the temperature to 0, I have an exponential ratio between the highest and the lowest exponential value. So this is how they look like. This is the condition number. So depending on the inverse temperature, the condition number of that matrix is very high. So now what I do here, for example, when I do the propagation, you see I have to multiply these matrices. And they contain exponentially large numbers, exponentially small numbers. And I lose accuracy doing that. Well, there was a method invented a long time ago. I think it's Gubernatis and others. I don't remember who the others are. We use that. So if we have the propagator, so these are different propagators of different times, we do an SVD on them, you see, according to this procedure, and then you don't lose precision. And instead of getting results which without SVD will look like this, so you definitely lose precision, we obtain that. So we have extremely good control on the accuracy of the results.
So what is beta?
Say it again?
What is beta?
Inverse temperature.
Ah, okay.
So the higher the temperature, the worse the problem is. And we want to go to low temperatures, not high temperatures. High temperatures are easy. I do virial expansion wherever that's easy. Okay? So this is another thing which is there. Here are the errors in particle number, but I'll talk a little bit about that too. Lattice artifacts introduce errors in another way. So if I have a non-interacting Fermi gas, where I have the dispersion, I have pairing gap, and I mean non-interacting, I mean non-fluctuating, mean field, simply mean field. Calculate the particle number. This is how I do it, right? Now I can take this and put a momentum cutoff. I'm still in the continuum, but to put a momentum cutoff. Or I can take this expression, which momentum cutoff is discretized. Okay? I want that, but actually this is what I'm using. So I want to know what's the difference between this and that. And here it is. As a function of particle number, number of lattice points, and here is the error in the particle number. So you see, if I take the particle number very low, basically you have to look at the blue curves all the time. I have a minimum somewhere here. And the reason is very simple. If the density is very low, the separation between consecutive levels is given by the inverse box size squared But if the particle number is too small, then can become comparable with the Fermi energy, or the gap, or whatever, something like that, right? So then I get errors, big. Now, if I start populating too much, I start feeling the cutoff, the upper cutoff. So the optimum is somewhere in between. So I cannot go to zero density, I cannot go to infinite density if I want to do that. I have to find this optimum. Now, if I increase the box size, obviously this goes down. Okay? So this is errors, you see, which come into the calculations. Now, a little bit more details about this. Typical lattice sizes, we calculate 8 to 16 cube. Number single particle wave function retains it's of the order of this number cubed. Number of time steps is basically thousands. So this is, if you put all together, it's much larger than lattice QCD, for example. You see the spaces. We use FFT because we work both in momentum coordinate space. So this allows us to simply get rid of matrices and so on. Calculation is very fast. Update field configuration using Metropolis. How we do this? We take this field and change the values. Remember, this is plus minus because it's discrete. So for that reason, we have relatively small fluctuations. We change that in order to have an acceptance rate between 0.4 and 0.6. Now, we thermalize at the beginning for about so many Monte Carlo steps. And the correlation time is typical like this. So we generate configurate, but then we have to move, you see, so many to obtain a new uncorrelated one. So if we do a million, for example, I say somewhere here we have millions of time steps. So it basically we end up with thousands, maybe hundreds, depending on the problem we are looking at.
So I'm trying to back out the temperature, but it's not there. So you said you do 1,000.
It depends on the temperature.
Okay,
So-
how
so-
much temperature can you go to in Hubbard units?
You ask, you see, I can tell you in Fermi.
Or what, I think
Yeah.
you said 1,000 slices. So how
Yes,
much the
yeah.
Hubbard-
You see, so now I have to give you the exact. You see that there are two things which control the time step. One is the strength of the interaction. One is the cutoff energy. Okay, so we choose the time step to be basically 1/10 of that, maximum of the minimum of the two. So we take the cutoff energy, divide by 10, inverse cutoff energy, divide by 10, inverse strength of the interaction, divide by 10, and that gives us the time step. And that gives us really good accuracy. I hope this answers more or less the question. Does it?
So inverse.
So the maximum energy scale, either the interaction or the kinetic energy divided by 10. I mean inverse, that divided by 10. Okay? Now results. And this is what was our first paper. It took almost a year to publish it for some reasons. But anyway, we calculate the energy as a function of temperature. This is the chemical potential. And I'll show you a little bit some other quantities too. Now, if you'd have a non-interacting Fermi gas, you remember now the theory that if you write down the energy of the ground state, it's the energy of the non-interacting Fermi gas times a number, right? Now, you expect that number to be smaller than 1, so take it down by whatever number. But if you can calculate that energy as a function of temperature, you can take a non-interacting Fermi gas as a function of temperature. We took that and simply shifted it down. This is the black curve. So we took non-interacting Fermi gas at a given temperature for given density, lowered it down in order to lie exactly on that. You see, for some reasons, you see above this temperature, there is almost, at least visually, agreement between the two. At some temperature here, it starts deviating and it goes lower. We couldn't go lower than this temperature, which is a little bit more, less than 0.1 inverse 0.1 Fermi energy. You remember that the scale of the problem is given by the Fermi energy, or the density. That's the only scale in the problem. So something happens here. At that time, we identified this as the critical temperature, which wasn't the right thing. And I'll explain that why. And this is the chemical potential. Chemical potential is the Fermi energy at 0 temperature, but then you increase the temperature for fermions goes negative and becomes the same thing as for bosons, so Maxwell particles. It crosses 0 at about 0.7 Fermi energy. Okay. Now we're trying to understand what is this behavior here. Now, since this is a Fermi system with attractive interaction, you might think that this could be either a gas of phonons, because if it's superfluid, you have phonons. And phonons is like black body radiation. Calculate, this is what you get. Okay? But then you have Cooper pairs. We know this from Carson, which was a little bit before us, right? Carson and the others. And you have to break them up, so you have the old Arrhenius formula with some prefactor in front. So you calculate the energy of those, exciting and breaking up the Cooper pairs. You do one, you obtain this curve. You do the other one, you obtain that curve. So we cannot go to very small temperature to distinguish between the two. And numerically here in this region, they're almost the same. Add them up together, they almost explain it. I'm not saying that this is an explanation. You see, it's kind of, you see, what it's probably happening there. So you expect in this system that, at least in this temperature regime, you excite with almost equal intensity, probability, whatever, phonons and break up Cooper pairs. This is a very unusual Fermi superfluid. It's not like helium-4, where you'll have only this. It's not like a BCS, where you'll have this. You don't have this in an electronic system, because the phonons become plasmons and they're much higher. So you don't have zero energy. You don't have Golson modes there. Okay? So this is a very unusual system in that respect. We calculated the entropy as a function of temperature, and also extrapolated later on the pairing gap at 0 temperature as a function of the inverse scattering length. So these are our results. These are Carson already. Sanjay sits there, you see, and there are all the results, but they done this temperature, this calculation during GFMC. So they work directly 0 temperature. We work the finite temperature, extrapolated, obtained that to, well, basically you agree with them.
Aurel?
Yep.
With respect to the previous figure.
This one?
Yeah.
Mm-hmm.
So when you have a lot of quasi-particles in the background, the phonons will be very strongly damped. So essentially, these phonons will decay quickly.
I'm not claiming this is a theory. I simply took non-interacting broken pairs, non-interacting phonons, non-interacting at all, put them together. If there is an interaction, there is some. Maybe that accounts, you see, for the slight disagreement, but I didn't worry about it. And this is true only when the temperature is significantly lower than delta. So this is not completely correct. And then the phonons, you see, at this temperature, the critical temperature, they don't exist anymore. So this, in principle, this formula should exist somewhere here, but probably not today. So you can criticize this formula, see how much you want, you see. So don't put too much in it.
The phonons are massless excitation,
They're sound waves.
and the quasi-particles, right?
Broken pairs,
They require a mass gap, delta.
delta.
So the two contributions are mutually exclusive. Either you have a mass gap or you don't.
No, you have, I'll talk about the gap too. You see, that separate discussion, it will be quite interesting too. Okay, so let's stop that for the moment. Now, there are high accuracy experimental results, not the only ones, where they measure the equation of state, I mean the energy as a function of temperature, or in this case, you can have the density at a given chemical potential and temperature as a function of the chemical potential over temperature. Because these are both proportional to the Fermi energy, you take the ratio, the system goes out. So this is dimensionless. So this is universal curve, in a way. It will apply to any system. Red points are experiments. Our initial results are this. You see the blue. It was done in a box which was A cube. Remember, it was the first calculation Monte Carlo I ever done in my life, together with Piotr, and that's when I became an expert. So, and we didn't have computers also. We have very small computers, serial computers until a couple of years ago. Joaquin, who was my student, and a bunch of others, I wasn't on that paper anymore, they calculated in a bigger lattice, I think this is 16, and these are the results now. So this calculation, it's actually a little bit earlier than that, but they never submitted the results. So it's here. Now, there are other results here which is these black things. This is the method which was developed by basically the people of Amrest, which is Prokofiev and Svistunov, and they sum up diagrams. It's called ball diagrammatic Monte Carlo technique. So it's a very interesting technique, but as far as it's implemented, it goes only up to the critical temperature, which is somewhere here, because they base that on propagators for the normal state, and once you go into the superfluid state, you have different class of diagrams, and they haven't done that calculation yet, so they have to redo. We, on the other hand, can go all the way through. Okay, so these are all actually old Burovsky result, which was 2006, you see, which we may claim at the time it wasn't very good. Was it me or something? That's you?
That's me now.
Okay. No, it's okay. Yeah, there is a new result. This one, I can't see. Oh, it's here. This calculates only the critical point. So it's only one point here. Now, you see that here there is agreement between the theory experiment basically at the level of 1%. So I think it's absolutely impressive when you see that. However, there is disagreement here. It's completely unclear why. Because theory has accounted for everything you can think of. It could be they don't measure the magnetic field accurately enough, or they do some other things, but this is very puzzling. You see this disagreement here. But anyway, the agreement with experiment and theory, it's pretty good. Yeah?
As far as I remember, the experiment done in Paris is more similar to the theory, but
The one in Paris basically goes through the theory. But they done high temperatures too, so it's here. There are too many results. You see, in the Unitary Fermi Gas, there are, I don't know, probably thousands of papers. So I cannot.
Well, it seems it follows the theoretical curve a little bit more.
Yes, yeah, but that's experiment. You had a question?
Is that the same discrepancy as on the left graph? Where the
Yeah, over here.
point is different than the extrapolation?
Yeah, because here is the energy, this is the density, so these are slightly different quantities, but they're related. Because they depend basically on one parameter, which is this. That's the only parameter at finite temperature. Yeah?
As you explained, the simulations are done with two cutoffs, the lattice spacing and the box size.
Correct.
We need to extrapolate to 0 lattice spacing and infinite box size. Is that done in this way?
That enters extrapolation. You see, you remember, so I have to go back, you see, to this plot. If I go to zero density, I go into that direction. If I go, you see, in the infinite, I go in that direction. So, you see, that's something, you see, which people can talk, you see, and it's a very delicate thing how to do. We can estimate the errors.
But you should not expect agreement with experiment unless you have done this experiment.
Yes, here there is a certain extrapolation done in the black, you see, this ones, to the infinite system.
Surely this data over there are, this theoretical data are for three lattices, so they overlap with each other, so it's like 10, 12, and 14.
Yeah, and so
You don't see actually much improvement when increasing the lattice.
so that was actually what was done. You see, we done several lattice size from, I think we started from 6 to 16. You see, we have different type of calculation, and we have what we call systematic errors. You see, maybe it's not so accurate as you do in lattice QCD, but we can claim safely that it cannot be outside these bounds, you see. And we are very generous with them. Okay. So at the moment, I think, you see, we are pretty good, you see, to be at this level of accuracy. You see, I don't think we need more. Yeah, you had a question? You see, you had a hand? Okay. Whoops, I think I'll have to speed up. This is the two-particle correlation from which we extract the critical temperature. And here I'll give you the results. And actually, there are two sets, you see, because here it's what we obtained, the squares, and this is what the Amrest ETH group, this is Svistunov, Prokofiev, Troyer, and a couple of other younger collaborators. You see, we have these points, they had that point, and one point here. Now, if you go to BCS theory, it will tell this. That's not strictly BCS because you have to introduce a so-called Melik-Bakhrudarov correction, so that's included, and then it will look like this. If you go to BC limit, that will be the critical temperature, and it's known that this has to rise a little bit from theory. So in principle, you'd expect the full calculation to have a maximum here. I think this is exaggerated in my opinion, but we don't have anything to argue with. We didn't do a calculation there, there is no experiment. So that's what we know. And this, I think, it's pretty solid. Okay. Now, about the systems. If you make a plot of the gap over the critical temperature, gap of the Fermi energy, and put all the fermionic superfluids there, known. BCS-like superfluids lie on this line. High temperature superconductors, they're here. Cold gases are here. Okay, so you see this is a very interesting system. Extremely large gaps, large critical temperatures, and this exceeds on the other side. What do we know about this? There is the so-called pseudogap. So let me talk a little bit about that, because there are at least 2 or 3 topics I want to talk about. Theory, what we do. In order to calculate various properties I'll be talking about, we'll need to calculate the Matsubara propagator. I think everybody knows what that is. That's related with the spectral function. We calculate this, we have to know this. And you see there is a problem, because this is known in a finite time interval, imaginary time interval. So if I want to do the inverse Fourier transform or something, it will be a problem. In order to do this, we apply 2 methods, maximum entropy method and singular value decomposition. I'm not going to say much about this. We know from theory about this, it satisfies certain restrictions. Integrates to 1, integrates to particle number, and it's always positive. When we do the determination of that, we use these constraints. Because we know that, we use these constraints, and then we invert this integral operator to find this quantity. Okay? We calculate in particular spin susceptibility, viscosity, and a few other things. Here to show you how well it works, you see here it's the green function, the Matsubara propagator initial and recalculated from what we determined to be the spectral function. And we do this in various ways, always come to the same result. So we have assumptions. For example, maximum entropy method, you have to have a guess. So a guess, it's 1 maximum, it's 2 bumps. Nevertheless, when we minimize, we obtain that result. We have error bars, because obviously this problem is ill posed, because we have less information here that it's in there. So when you invert, obviously, you don't have all the information. So if you want to think in terms of Fourier modes, you don't have all of them. This is the error bar due to that. Okay, so this is the spectral function. I think this, no, this is not spectral. This is conductivity in this particular case, but this is the error bar. Okay. This is the spectral function here. So I'm sorry about that, you see, but I simply want to show you, see how it looks in principle, you see, not to go into technical details. So I think we do have a certain control. There is certain error bars. It's not perfect, but you cannot expect to be perfect. You see, I don't think it can be done perfect. Now, if we calculate this spectral function, here it's slightly on the BC side. We have similar spectra on unitarity. We obtain this. Below the critical temperature, this is energy, this is momentum. At the critical temperature, well above the critical temperature. Above the critical temperature, you have 1 single mode. This is a normal system. And you have energy as a function of momentum squared. This is a line, right? At the critical temperature, on normal Fermi BCS superconductor, this gap is closed. Here it's not. This is the pseudo gap. Here is below, you say you have the occupied or the whole states and the particle-like states. These are the 2 branches, you see, if you think of the Bogoliubov spectrum. Okay? From there, we can estimate, for example, the size of the gap, you see, by fitting this maximum, you see, like this. And this compares with what Carlson and Reddy have done a while ago at 0 temperature. So you see at critical temperature and at 0 temperature, they don't differ much. Okay? If you look at the pairing gap as a function of temperature, and this was at unitarity, it goes like this, drops to about half the value, and then it drops to 0. The critical temperature is here. So the critical temperature, there is a gap. This is the pseudo gap. What's the physics of that? Oh, I'll tell you about the experiment in a bit. If you have a BCS superconductor, the gap as a function of temperature behaves like this. If you go all the way to the other side, the gap basically is insensitive to the temperature because you have both molecules which are tightly bound. You see, you increase a bit the temperature, they're still tightly bound, and that's it. The unitary gas is somewhere in between, so you expect something like this. This is the gap everybody talks about. This is the actual gap you see. So this is the region where you see the pseudo gap. If you look at the density of states as a function of temperature, this is energy and this is density of states. At zero temperature, they look like this. This is not zero temperature, 0.12. This is red is the critical temperature, so you see a big dip. If you'd have a normal Fermi gas, it will be like the dashed line, which you observe only at very high temperatures, or relatively high temperatures. So why this difference? Unlike a BCS superfluid, when you reach the critical temperature, you don't destroy the Cooper pairs. This superfluid, it's not all the molecules condense into zero momentum states. You have a significant number above. So you simply have a gas of these molecules still existing. Some of them are broken, but you still have a lot. And this shows in the gap. You didn't break them all. Okay. There are experiments. My opinion, quality is not very good, which kind of confirm the existence of this pseudo gap. So I'm going to skip that. We map this as a function of temperature and coupling constant. So this is the critical temperature. This is where the gap disappears, and this is the so-called T star. So this is the unitary regime. And this could be interesting because, for example, neutron stars could be in this region. So they can influence the physics of the neutron stars in principle. Whether it will do or not, we don't know the answer because this is actually still a model. It's not quite accurate neutron matter. So I told you about that. 2 more slides and I'll be done. One thing which was also calculated is the shear viscosity. You probably heard that there was a lot of discussion, especially about the quark gluon plasma and after the work of Son and his 2 collaborators, that the shear viscosity has a lower limit. That lower limit, it's somewhere here. Okay? And the quark gluon plasma is the perfect fluid because it has a viscosity almost reaches this KSS Kovtun Starinet Son limit. We calculated this by looking at the response. So as we did, for example, for spin susceptibility, which I'm going to show you in a second, you see like this, but using the stress tensor. And this is how you calculate the viscosity. As a function of temperature, goes like this. Critical temperature is here, and you see there is a significant dip. Now there is a region here which is yellow. At very low temperatures, the superfluid thermodynamics is dominated by phonons. And phonons, you see the cutoff in temperature depends on the size of the box, you see, because obviously the lower the temperature, the lower the energy of the phonons, and we don't have big box. So we had to include the contribution of those phonons from theory. There is an effective field theory of phonons in a superfluid. And their contribution is this one in yellow. So we added it, and this is what comes on top of our results. Basically, the contribution comes at very, very low temperatures only. But even with that contribution, you see that the phonons, you see, above this temperature, they don't essentially contribute. So the limit is not quite obtained because that limit is 1/4 pi, which will be something like 0.08. It will be here. This is about 0.12, 0.15, something like that. No, Piotr, what's the exact number? Yeah, you remember? But no, that number it's actually not for this. This is entropy over density. That's entropy over entropy density. So it's not the thing. So this is the last thing which I'll talk about, the spin susceptibility. We have an external field which acts on spin up in one direction and spin down in another direction. So basically, if I have them in a pair, I break the pair. Right? And now I look how the system responds as a function of temperature. If I'm at 0 temperature, I cannot break them. Right? Because it's linear response, it's a weak field. If I'm at finite temperature, well above the critical temperature, the pairs are already broken, so there should be no effort doing this. And I can calculate from normal Fermi liquid properties. This is this result, the dash and the solid lines. Now, if I want to break a pair, this is kind of a local probe. It doesn't probe the coherence in the superfluid, which is long range, which at the critical temperature goes to infinity. Right? So I probably said something very local. So now if you look how this spin susceptibility goes, it goes from 0, goes to the critical temperature very smoothly, it doesn't care. And it becomes that of a normal Fermi fluid at temperatures well above the critical temperature, basically where the pseudo gap disappears. So this is consistent with the fact that in a unitary gas, pairs survive, the Cooper pairs survive the critical temperature, unlike the BCS. They exist at finite temperature. And this is an experiment actually was done. And this is where the experiment is. That's it. Thank you.
Regarding this figure, have you tried to see if the quasi-particle picture provides susceptibility, because the thermal quasi-particle doesn't?
The Fermi, you see, Fermi liquid theory gives you this. There are two.
I'm not talking about the Fermi liquid here. I'm talking about the gap quasi-particles that are thermally excited.
Well, we've done a full calculation. You want us to do a simple calculation? We haven't done that.
The analogy you gave us earlier on
I know.
how well the quasi-particle picture.
Well, it was in the first paper, you see, but it was only about the energy. So in this case, you see, I don't know, I would have to do the spin susceptibility of a gas of molecules and atoms. This is what I would have to do. And basically, I'll be somewhere above the, you see, somewhere around the ionization temperature. You see, the critical temperature, ionization, what I would call here, you see, when you completely break the pairs, it's somewhere in this regime. So I'd have to have a theory of that. Well, I don't know if it's worth the effort in doing that. I don't know, maybe, but we haven't done it. Yeah. Yeah.
You can study a unitary Fermi system also in one spatial dimension. And if you do simulations, apparently it turns out that the ground state units of the Fermi energy is the same as in 3 spatial dimensions. Do you have a comment about that?
I never cared much about anything except 3, honestly. And the reason is because this is real world and it applies to nuclear physics, and I kind of want to think a little bit of what I can learn from this, you see, to transfer there. And I cannot think of 1 and 2 dimension in nuclear physics. You see that? No, and I believe, you see, that comes, you see, so this is not a complete answer because I didn't think too much. I think if you take a zero-range interaction and vary the number of dimensions, the energy of the system goes to the energy of the free system in 2 dimensions, and in 4 dimensions it goes to minus infinity or something like this. This is what the analysis of Son and his collaborators Nishida actually showed that. You see that when you reach 2 dimensions, actually the interaction is perturbative. It's so small, you simply don't care. So if you continue all the way to 1 dimension, I think it's something else. I think there you are dealing with the so-called a system which is treatable through beta ansatz. The level density in one dimension is totally different from the one in 3 dimension. In 3 dimension, as a function of energy, the level density increases like this. In 1 dimension, I think it's just the opposite. It increases towards 0 or something. I don't remember. Yeah, I think that's the way it does. You see, it's completely different physics. And so I think, you see, something else will happen there. But then you can have quasi-one-dimensional system. You take the 3-dimensional and start squeezing it like this. I don't know exactly what happens there. You see, I know some people try to think of that, but basically you froze 2 degrees of freedom and allowed motion in this direction. But at that point, I think fermions becomes impenetrable. So basically, the fermions and bosons looks almost the same because they arrange the same in like beads on a string, and they don't go past each other. But I don't know a lot about it, the limit. Okay. Okay.
Okay.
Thank you. I'll think.
Yeah, it's taking a little bit to go.
Okay.